the abbreviations like OCDS, OTGB, and OTGM, and, more importantly, why you should care about this module to enhance your debug experience. Then, like in the previous sessions, we use a more or less realistic example application to demonstrate how to utilize the capabilities of the OCDS Trigger Bus for hardware tracing. We start by revisiting our old friend, the DMA controller. The DMA module is one of about a dozen peripheral modules that are observable via the OTGB. The available status information depends on the peripheral. In the case of the DMA controller, we can look at active move engine and channels, errors, and transaction requests. Next, we measure interrupt latencies. In previous webinars, we have shown how to record ISRs using OS profiling or program flow trace. However, these techniques only show us when an interrupt service routine executes, but not when the hardware interrupt request has occurred. Luckily, the OTGB can give us complete insight into when a specific interrupt request happens in hardware, and how long its arbitration takes. Finally, we demonstrate how to trace the output signals of a high-voltage DC-DC converter application. A clever way to analyze the application's functionality without the need for external hardware like an oscilloscope. As usual, we end with a short conclusion and time for questions and answers. Let's start by going over the abbreviations that will haunt us throughout the webinar. We have summarized all abbreviations in this table for reference, but let's go through them one by one. Firstly, OCDS stands for On-Chip Debug Support. The OCDS is not a single module, but an umbrella term for all modules on the AURIX that facilitate debugging. Infineon calls the main debug module Cerberus. It enables run and stop control, access to SFRs, and other features required by hardware debuggers. Next, the OTGS, or OCDS trigger switch, consists of 7 independent trigger lines. The OTGS collects debug events from various sources such as CPUs, buses, and peripherals, and distributes them to CPUs, DMA, and trigger output pins. Trigger output pins are a set of packaged pins that can function as inputs or outputs for the trigger lines. Lastly, we have the OCDS Trigger Bus, OTGB. The OTGB is the module we care about in this webinar. It collects interrupt requests and peripheral status information via so-called trigger sets. Trigger sets are a collection of relevant signals for a specific peripheral. Additionally, there's also the OTGB-M, where the M stands for MCDS. The OTGB-M is a dedicated trigger bus for the GTM module and only connects to the MCDS. We can route the OTPG data via the OCDS Trigger MUX, either to the OCDS Trigger Switch or the MCDS. Routing to the trigger switch allows putting a peripheral signal onto a device pin, which is helpful in cases where the MCDS trace system is not available. However, this webinar series is about tracing, so let us look at how the OTGB and OTGB-M connect to the MCDS, the multi-core debug system that contains the trace logic of the AURIX. If you have forgotten what we want to do after hearing all the abbreviations, that's okay. Let's recap. We have peripherals that may be hard to debug with regular start and stop debugging. Luckily, many peripherals have so-called trigger sets. A trigger set is a bit vector that makes relevant peripheral signals routable to the OCDS Trigger Bus. The Trigger Bus connects to the MCDS, which allows us to trace the signals, meaning we can observe the status of peripherals over time, hopefully making debugging much more effortless. Now, there are two 64-bit OTGB buses. The first one consists of 3 sub-buses, OTGB 0, 1, and 2. 0 and 1 have 16 bits, and we can overlay trigger sets from almost all peripherals onto them. OTGB 2 has 32 bits, and only supports the E-Ray's trigger set. E-Ray is the FlexRay protocol controller, and we will not further talk about it in this webinar. The second 64-bit bus consists of OTGB M0 and 1. The OTGB M only supports the 32-bit overlays of the GTM module. Let's see how the OCDS Trigger Bus connects to the MCDS, and everything should become clear. Here's a block diagram that visualizes what we have discussed until now. There are two peripherals, A and B, exemplifying any of the peripherals shown on the previous slide. The peripherals make their relevant signals available via trigger sets. For each of the peripherals, we can choose which trigger set to map onto which bus. For example, we could observe two peripherals in parallel, or two trigger sets from a single peripheral. Note that the OCDS trigger marks ORs the signals from different peripherals, meaning we have to make sure that only one peripheral connects to either of the 16-bit OTGB buses. Otherwise, it becomes impossible to interpret the data, except if we know that each of the OR trigger set uses a different set of bits. Luckily, OTGB2 and M only accept trigger sets from a specific peripheral, the E-Ray and the GTM respectively, so we don't have to worry about enabling too many trigger sets for them. Lastly, at the bottom, you can see that the interrupt router also connects to OTGB 0 and 1. This so-called interrupt request overlay provides a couple of additional 8 and 16-bit trigger sets that facilitate monitoring active interrupt service requests and interrupt arbitration information. At this point, we understand how we can route peripheral data to the MCDS. The last piece of the puzzle is how to record the data. If we look at the MCDS, we can see that POB0 and BOB-SRI can observe the OTGB. Similarly, POB0 and POB1 can observe the OTGB-M. POB stands for Processor Observation Block and BOB stands for Bus Observation Block. We have explained these blocks in detail in the previous parts of this webinar series, so please watch those if you're not familiar with the terms. For now, we only need to understand that the observation blocks have access to the OTGB data. Within an observation block, the MCDS accesses the OTGB data via the data trace unit. Consequently, we can use all the DTU features like value triggering, masking, comparisons, and more complex trigger conditions to process the peripheral data. Lastly, we should note that the MCDS qualifies the number of relevant bits in an OTGB message via the message's address field. The MCDS uses the address 0 for messages that contain 32 bits of data and the address 8 for 64 bits of data. Okay, that was a lot of theory, but by now you hopefully have an intuition for why the OCDS Trigger Bus is powerful and what its building blocks are. Let's see how we can use it, either to debug our application like a pro or to impress our colleagues with expert AURIX knowledge. We will give you examples for DMA, RIQ, and GTM tracing in a second, but first we want to provide you with a generic recipe for OTGB tracing. So first, well, you have to know the peripheral you want to observe. Then, for that peripheral, find the OTGB interface section in the TriCore user manual. That section lists the available trigger sets and the signals they make available. Once you know the trigger set you want to record, find the OCDS Trigger Set Select register for the same peripheral. Use the OTSS register to select the trigger set you have chosen and specify the bus onto which you want to overlay the trigger set. You can configure the OTSS using a Vinode initialization file, manually set the values in the SFR view, or write to the registers from your application. The initialization file is probably the most straightforward approach. You also have to make sure that all bits of O-P in O-N are 1. These are the MCDS interface edge sensitivity bits, and by setting them all to 1, we say create a new OTGB message whenever any one of the trigger set signals changes. With that configuration in place, you can configure the data trace for OTGB. Lastly, you have to configure the WinID analyzer to make sense of the recorded OTGB data. Since every trigger set is different, you have to configure how to interpret and visualize the data. Okay, let's follow the recipe to observe the DMA controller with the WinID analyzer. If you go to the OTGB interface section for the DMA module, you will find that it provides 10 trigger sets. The first 2 trigger sets are performance and error, and then there are an additional 8 channel trigger sets, each covering 16 channels. Let's say we want to analyze the general performance of our DMA controller. That means we have to configure OTSS trigger set select so that it chooses TS16PF. Additionally, we have to use OTSS bus select to route the data to one of the buses. We use a WinID initialization file to do the configuration. If you're not familiar with the syntax, we use A followed by the address or the register's name, and then an L for long integer, followed by the value we want to write into that address. As you can see, the lowest 4 bits map to TGS. The performance trigger set has the ID 1, so we set these 4 bits to 1. Bus select is bit number 7. We configure that bit to 1, which outputs the trigger set on OTGB 1. We also configured the edge sensitivity bits so that any change of the trigger set creates a trace message. Now all we have to do is add the ini file to the initialization sequence under Hardware CPU options. We also want to make sure that WinID initializes the OTGB for downloads and debugging. And make sure to do a download or load symbols to apply the new initialization file. Alright, time to record a DMA performance trace in the analyzer. We have an existing configuration that uses ticks as the timestamp source. The previous webinars of this series explain how to create such a configuration in great detail. To capture the OTGB data, we can use PUBX or SRI1. We go for the latter. At this point, the data trace unit connects to the OTGB. So all we have to do is enable data recording by setting write data and write address to always. And sure enough, when we record a trace, we see DTU messages at address 0, and it seems like only the upper 2 bytes are changing. That's what we expect since we're only using OTGB1 at the moment. Next, to visualize the data in the timeline, we create a data area. We give it a meaningful name and map it to address 0. We only care about the upper 2 bytes, so we change the size to 2 bytes and specify an offset of 16 bits. If we rerun the analysis by pressing the blue recorder button, the analyzer shows the OTGB messages in the timeline. Of course, the raw values are still not too helpful. We need to decode the messages to make sense of them. To decode the messages, we first need to understand the 16 bits DMA performance trigger set format. Our trusty friend, the TriCore user manual, tells us that each byte maps to one of the 2 move engines. The highest bit for each move engine indicates whether it is idle or active. The remaining 7 lower bits indicate the active DMA channel. Equipped with that understanding, we can use the Swiss Army knife of the analyzer, profiler inspectors, to implement a decoder. First, we create 2 events, move engine active and move engine inactive, that trigger when the move engine bit is 1 or 0 respectively. Next, we create a simple state machine with the default state ME idle that moves to ME active when the active event occurs and back to idle for the inactive event. Finally, we create a variable that masks the lower 7 bits and gets updated for each ME active event. As you can see, I have 2 inspectors already in place. So it's time for a drum roll and the final result. Very nice. Not only do we now see when a move engine is active or inactive, but we also see the channel it is using. Let's take a moment to appreciate the result. We have learned how to tell the DMA module to output the performance trigger set through the OCDS Trigger Bus. Then, we have configured the MCDS to record the DMA messages using the data trace unit. Lastly, we have told WinIDEA how to interpret and visualize the data in an intuitive way. Let's take a deep breath, and then we add interrupt service requests into the mix. The interrupt request overlay consists of 2 8-bit trigger sets and 2 16-bit trigger sets. The 2 16-bit trigger sets, TS16SP, are identical, except one can only map to OTGB 0 and the other one only to OTGB 1. They allow monitoring the last arbitration winner for a specific interrupt provider. An interrupt provider can either be one of the CPUs or the DMA module. Additionally, a dedicated bit shows if one or more interrupt requests are currently waiting for arbitration. The limitation of this trigger set is that it only shows us when an interrupt request has one arbitration, but not when it initially occurred. In other words, when multiple interrupt requests are pending, we won't see how long each of them is active. If we want to observe pending interrupts for all service providers, we can use TS8SPA, where SPA stands for Service Provider Activity. It uses 6 bits to indicate whether one or more service requests are pending for each of the CPU cores, and then another bit for DMA interrupt requests. Lastly, the trigger set TS8 interrupt selection shows active interrupt requests for any of 4 configurable interrupt service nodes. The main difference to the other 2 trigger sets is that it allows us to see if 2 or more interrupt nodes are waiting for arbitration by the same interrupt provider at the same time. In other words, it enables us to detect delays caused by high interrupt load. Additionally, we can use TS8IS to measure the time between an interrupt request and the response of the interrupt service provider, for example, the execution of an interrupt service routine. Let's add the IR overlay to our existing configuration of the OTGB. The IS overlay has 8 bits. Consequently, we can map it to 4 locations on the OTGB, the upper and lower byte of either OTGB 0 or 1. We have already mapped the DMA trigger set to OTGB 1, so only OTGB 0 is available. We configure the IR overlay via the OIX trigger select register, as before, via an initialization file. First, we select the trigger set by setting TGS to 1. Then, we overlay the trigger set on the lower byte of OTGB 0 by setting OBS to 0. Now, the second part of the configuration is a little trickier. We have to specify the index of the service request node we want to observe via one of the 2 OIXS registers. Each register takes one SRN index from bit 0 to 9 and the second from bit 16 to 25. If an ISR services a service request node, the most straightforward way to find the SRN index is to set a breakpoint inside the respective ISR. For example, here we put a breakpoint inside the GTM Tom1 ISR. Once we have stopped at the breakpoint, we can read out the index of the service request node via the last acknowledged service request register. The ID field contains the value we want to write into OIXS. As you can see, we have configured 4 service request node indices in total. For each SRN, the OTGB signals when it is pending and when the service provider clears the pending flag. Lastly, we have to make sure that the sensitivity bits are still active. We have already configured these registers in the DMA initialization file, but it doesn't hurt to do it a second time. And it guarantees that the ini file will work standalone. We have already configured the MCDS to record the complete OTGB. Therefore, we only have to add another data area covering the lower 8 bits of the trace messages in the analyzer. At this point, we can do another recording and observe both DMA and IRS signals in the timeline. As before, looking at the raw data is not too helpful, so we have to look at the trigger set encoding of TS8IS. Each of the 4 selected interrupt requests has a bit that tells us whether it has a pending request or not. Again, we can use WinID's bit masking feature to create a data area for each bit. The description field contains the name of the service request node that maps to the particular bit. And under layout, we specify the size of one bit and the offset for the respective interrupt request node. Additionally, we add a header file that maps the value 1 to the string pending and 0 to the string idle. The analyzer will then show the respective string in the timeline. Let's enable data areas for all service request nodes and then do a reanalyze to look at the result. As you can see, there's now a separate area for each SRN. By expanding the objects, we can see when the pending flag is active. With that configuration in place, let's interpret the interrupt request data. I have slightly extended the analyzer configuration to record the interrupt service routines that service the interrupt requests via program flow trace. That makes it easier to understand what's going on. I have also removed some areas from the timeline to make it less crowded. The rest of the configuration is identical to what we have just configured. So let's zoom in at about 400 microseconds. As you can see, at this point the DMA move engine 0 is active on channel 2. After around 2 microseconds, the DMA transaction is complete. At the same time, the DMA channel 2 ADC interrupt request node becomes pending. It seems like the DMA is signaling that it has successfully read some ADC data. After an additional 4 microseconds, the interrupt request is serviced by the ADC DMA transaction complete ISR. The OTGB gives us complete insights into the data flow. What's maybe more exciting is that after another couple of microseconds, the interrupt pending flag for the timer output module service request node becomes pending. Apparently, the ADC DMA ISR has a higher priority, so only after it has finished execution, the TOM 1 millisecond ISR can service the request. As expected, that clears the IR pending flag and the request node goes back to idle. Alright, and with that, I hand it over to Matthias, who shows us how to record GTM signals with the OTGB.
Hello and welcome also from my side. Today I have brought a DC-DC example application that I got from a colleague. It showcases a few things quite nicely, which I want to explain today in a bit more detail. Let's first start describing what we have here. So on top we have the interrupt service routines here, which you can see are occurring nice and regularly mostly. And below that I have the DMA tracing that Felix did introduce in more detail earlier. And then below this I have a few signals that look like logical signals, but in the end those are the PWM signals that are controlling the outside switches for this DC-DC regulator. So basically, I have all my signal flow in one view. I have here the control interrupt service routines where the control loops are running. I have the DMA transfers that show when my ADC results are available or when my timers are updated. And then finally, what I also have is a detailed view of all my timing signals as they are present on the outside. The question is now, how do I do this without attaching any additional wires in my setup? Because you can see my setup here. It's just an active probe from iSYSTEM with my connected to my IC 5700 and my tri-board with an Infineon AURIX, but it doesn't have any additional logic analyzer, no oscilloscope, nothing is connected besides my IGBT cable. And exactly this question I will answer today in this session. To start this demonstration, let us first check what setup we have in our AURIX. This software represents an example use case for a high voltage DC-DC. The setup uses CPU 0 for all software execution. The main portion is the initialization of the chip. Afterwards, only small interrupt routines for the control loops are required. The timer output modules within the GTM generate the PWM outputs with the configured duty cycles. The port logic to the pads, which drives the outputs towards MOSFETs or whatever is connected here, then routes those PWM signals. To generate the required input for the control loop, the EV-ADC measures the currents. The CPU does not handle data transfers, but the DMA, to make sure we save precious CPU time from being wasted. And lastly, the system timer is generating our timer ticks for the cyclic interrupts. Not related to tracing at all, but surely worth to note is that the interaction between TOM, ADC and DMA does not require any CPU time. Now that we have a rough overview what modules are involved with our application, let's inspect the interconnect signals. First, here on the top right, there is the PWM output connection from TOM, from the timer output module, to the output pins. This is the output signal that is driving the switches for the voltage control. Next, here in the middle of the picture, the timer channels are additionally driving the trigger signal for the EV-ADC to trigger the ADC conversions start synchronously to the PWM generation. And last but not least, here is the main part of today's demonstration. There is an internal connection from the signal output of the pins towards the timer input modules of the GTM. The question is, what is this good for? I will show you now that this signal can be sampled using the OTGB. This generates trace messages containing the logic signal level of some timer channels, input and output. Effectively, what we do is we monitor these signals on the outputs without connecting any external wire, as you have seen on the photo. No soldering, no fiddling with scope probes and scope settings. And the best is, it is fully synchronous with our software and DMA trace. Enough of the advertising and theory, let's get to the hands-on. So let's first have a look at my workspace. As you can see, I have a source file here, CPU main, that contains a lot of initialization code. I have the peripheral view for some peripheral registers. You can see I called it peripheral trace. So it's only a sub-selection of a few registers that are interesting for this webinar. Note that you can drag and drop those from the normal SFR view into a custom view. I use this because it's much more convenient. If you just have what you need in one view. I have a watch window with a single variable that I can set to enable more software activity and then DMA activity. And then we are basically good to go. What we need to do is enable a few things in registers. Of course, you can outsource this to an ini script like in the previous webinars, but today I want to show you how that's done manually. So any peripheral that has OTGB connection has one of those OTSS registers. So the GTM does as well, and here I want to put the data to OTGB1, so I need to select here the trigger set correctly, and then I go to the GTM OTSC0, where I can select what data the GTM should put there on the OTGB1. Here I select both 2 times TIM modules with each 8 signals. Here TIM2 and here it's TIM3. And I enable as well the DMA OTSS, and then of course I set the OMIS-N and OMIS-P registers to all Fs, and make sure that your GTM is enabled when you're trying to access any GTM registers. So the GTM CLC register should show a 0 value here. Otherwise, your register accesses will fail because the GTM doesn't have any clock supply. Now, if we go to the analyzer view, how do we create this configuration? Let's have a quick look at the configuration that I created here. So I have, I have a manual configuration here. I'm using process observation block X for the OTGB. I'm using process observation block Z for the CPU 0. I use time source tick. I just changed that. And then for the POBX, I'm using the right data and the right address. TriCore Y POB I'm not using, and for the Z I'm having the program trace unit enabled to set to always. On the MCX tab I have the ticks enabled. That's the main thing to be done here. And then we are already finished with this part of the configuration. Then what we would get in the end is only the software and nothing else. So what we still need is in the profiler area, we still need an additional data area. Here I gave it the name OTGB data raw. It's location 0, since the address will be 0. We will look at all cores. Its size of 4 bytes, and that's it. And then we would get, if we have configured this, what we would get in the end is a view that's more like this here. And from what I'm showing here, you can already see that this is a bit less useful, let's say. So we are going to change that with inspectors. We have already introduced you to those DMA inspectors here, but here we have additional inspectors for the GTM, which I want to show you quickly here. So for the GTM, we have for each bit one inspector to have those bits, because basically on the OTGB, 1 bit in this upper part is corresponding to 1 signal on the GTM inputs here in our configuration. So we are having a decoding for those, or a visualization for those for each bit separately. So we have those as separate signals, as you can see down here. So you can see I have all those inspectors in here. They're basically all the same. And if you want to quickly get them, you can use a JSON file for those. I've exported them, and I think you can get it through Felix at iSYSTEM. So now that we have all of this, the result should basically look like this. So let's do a new trace. see if everything works. It takes a while for analysis. My PC likes to take his time on this. And it will conclude soon, hopefully. We can already inspect the OTGB data, so we can see there has been a lot of data recorded, all the different values we can see here. But of course, then with the inspectors, it makes much more sense. So now if you go into those signals, you can really see that you can already see the dead time in between those here. We can quickly measure this, now come on. So using the cursors, you can quickly measure this. So this is now 640 nanosecond, and so on and so on. And now what you see is that you can get all those things here and really inspect if anything is aligned in time. Yeah, you can see that those interrupt service routines are obviously aligned to those edges here. There are DMA transfers happening, and what you can get now is all the timing relations. So you can set a cursor here, and then if you're interested how the delay is to this DMA transfer as an example, then we can measure even those. So this really gives you a good overview over the whole application.
Fantastic. Thank you very much, Matthias. That finishes our demo for today. We hope this demonstration has been helpful for you all and that you can soon utilize the power of the OTGB for your projects. We are now available to answer your questions. And with that, I give it back to the moderator.
Thank you, Felix. Thank you, Matthias, for your demonstration, for all the information. This is really, really interesting and very powerful what Infineon provides on these AURIX controllers. All right, Felix, you said at the beginning, I think, that the OTGBM is used only for the GTM module, but I think you used the OTBG module, OTGB module, sorry. So why didn't you use the OTGBM?
It's crazy with all your abbreviations, isn't it? Yeah.
Yes.
Yeah, so initially I actually thought that Matthias was going to use the OTGBM for the I/O recording, but the GTM actually has 16-bit trigger sets and 32-bit trigger sets. And so the I/O trigger set that Matthias has demonstrated map is a 16-bit I/O trigger set, and that maps to the OTGB. So that's why we use that one. But in addition to that trigger set, there are an additional 14 32-bit trigger sets, and those can only be recorded via the OTGBM. So I guess that would be like another webinar if anybody's interested in observing the GTM in great detail. Honestly, I don't even know what all those 32-bit trigger sets are even doing.
So you have some time to learn that until the next webinar.
Exactly.
Wonderful, thanks, Felix. I would like to stick to the topic GTM in a way. So Matthias, the GTM, DMA, and software trace, can I observe more than one core? So the AURIX is a multi-core core with up to several 6 or even more cores. Is it possible to also view more cores?
Yeah, even in my setup, you could view one additional core, since I have one processor observation block left. And then what could also be done is switch the OTGB to one of the SRIs or crossbar observation blocks. And then you could even trace 3 CPUs plus the OTGB. Yeah, so all of that would be possible.
Okay, cool. Another question I have goes out to Felix again. Felix, you explained how to find the service request node index by setting a breakpoint into the respective ISR. How can I find the index if the service request node is not serviced in the software?
Yeah, so all the service request node has src underscore name of the respective service request node, so service request node configuration register, and like those are all in like a continuous memory section. And basically what you do is like you take the src register of the service request node you're interested, and then the index that you're looking for is the offset from the to the first src register. So basically the first src register has the index 0, and then like after an additional 4 bytes, that's service request node index 1, and so on. So basically you take the offset in bytes, divided by 4, and that's how you could calculate the index for any service request node.
Wonderful. Matthias, anything to add here?
Yeah, I still think it's easier if you go to the user manual appendix and just check out the table there, because then it's all nice and ordered, and you just need to Control F search for your peripheral, and then you get directly the offset.
So it's not the user manual, but the user manual appendix, right? This is a different document.
Yes.
Okay.
Exactly. That's device specific. Yeah. So for your specific device, there is a user manual appendix, while the user manual is applicable to all devices.
Okay. So different document. Check that for more details for that.
See, I actually didn't know that, so maybe that's why I calculated by hand all the time. So yeah, it's good. It's good to have an expert in the room, I guess.
Yeah. Read the documents. Yeah. All right, Matthias, I would like to come back to the PWM. I think, so at least for me, it was not clear what was the resolution of the input signals of the PWM pins.
Yeah, so the MCDS runs on 150 megahertz, so it's not going beyond that. But for a general impression, that should be fine from my point of view. And the GTM basically samples it with 200 megahertz.
Okay. So I have no questions left. Sorry?
No. Was just an addition that it doesn't completely, let's say, replace an oscilloscope, but still it's way more convenient than an oscilloscope, since you don't need to attach anything physically. Mm-hmm. So the solution is resolution is a trade-off.
Okay, so I have no questions left. No questions came in, so either everyone is impressed or depressed, either way. So thanks again, Felix and Matthias, for sharing your knowledge. Thanks for being here for questions or answers. And let's come to an end. And dear audience, before you leave, I would like to ask you, please leave us your feedback in the polls to improve our webinars, to learn more about how you like it. Check out also our online trace tutorial on the iSYSTEM webpage, the application notes, and the other webinars available on the YouTube channel. As this is session 3, of course, session 1 and session 2 is also available. And if you want to, feel free to register to the newsletter, then you get webinar updates or invites automatically. So if you have questions later, feel free to send them to webinar@isystem.com or reach out to your sales or tech representative at iSYSTEM or Infineon, of course. Felix, Matthias, thanks again. Thanks for sharing your knowledge. See you next time. Bye and take care.
Thank you.
Bye, everybody.
Have a good day.
Thanks
Bye.
so much.